Representing motion information, encoding from displacement versus time, d versus t, to velocity versus time, v versus t. Hello! Hey, so what we're going to do is the following. We are going to convert this graph over here, which is displacement versus time, to this blank one over here and encode the information, the motion information, as velocity versus time. All right, so to do that, we need to realize that our definition of velocity, which is over here, is that the change in displacement over the change in time equals d minus d naught over t minus t naught. This is the definition of velocity. It also indicates something else, that it is, in fact, as we know, the slope. So this guy over here is the slope of a d versus t graph. We notice that if we look at the rise, we have meters, the run is seconds. And so the slope represents meters per second, like that. So if we read the slope to get our velocity, if we try to figure out the slope here for every interval, for example, then we can encode that information somewhere down here. And so that's what we're going to do. Let's try that out. All right. Clear our workspace. Beautiful thing. All right. We'll do the first interval from 0 to 5 seconds using the straight up definition over here. Well, what we have is d minus d naught. We have 40 meters over here. This is where we went to. And we started at the origin, so it's 40 meters minus d naught, 0 meters. Divided by the time interval, 5 minus 0. So it's 5 seconds minus 0 seconds. And what we get is 8 meters per second. So what I'm going to do is encode that over here in velocity versus time. And to do that, I'm going to try to put an arrow, let's see, or some kind of marker over here to do that, a line. There we go, there's our line. We can draw it again. So at 8 seconds. Now notice also that because the slope over here is constant, this guy is a constant slope, what we also notice is that down here, this has to be constant as well. The velocity in the velocity versus time graph has to be constant. So we have a constant slope, therefore we have a constant velocity. And so this is a straight bar going across, whose value is 8 for the entire interval. Some of you guys got that very well on the quiz. Others struggled a little bit and actually made some connection points and changes, but we're going to be okay now that we got the concept straight. Constant slope means constant velocity. Let's do the rest of the intervals. So the next one is this. Ooh, look at that. I want to go with my pen tool. The next one is this interval over here. Okay? And for that, we are going to move from position 40, or displacement 40, to displacement looks like 30. So we have 30 as our going to, 30 meters, minus where we came from, 40 meters, divided by the time interval. Now we know the time interval is 5 seconds, but I'll show you again why that is. It's 10 seconds minus 5 seconds. Altogether, this equals negative 10 divided by 5. Okay, and the units are meters per second, which equals negative 2 meters per second. So now I'm going to try to encode that also. Go back to v versus t, and what I should be able to do is draw that out over here to negative 2. All right, negative 2 horizontal. So now I'm connecting. Now, this sharp point means that we have some sort of instantaneous change in our velocity. That's not really possible in the real world, but for this exercise, we're just going to say that this velocity here changed from 8 meters per second positive to negative 2 meters per second instantaneously because of this sharp point. Later, we'll be able to smooth them out and understand what that means. Okay, so going with the next interval, it's very easy because that next interval, as I clean my board over here, is 10 to 15 seconds. It's a zero slope. We have a flat, constant displacement. We're not changing our position. Therefore, that means we'll just go to 0 meters per second. You can do the math out in terms of the actual definition, but there we go. This is 0 meters per second. Now I could probably draw it a little better so that it's on the line like so. All right, the next slope. I'm sure I can do this. There we go. Next, we have an interval that is a negative slope from here. And it's going to go, from, it looks like it's going to position negative 20. And it's from 30. So what we have here is minus 30. And what we have is negative 50 meters over 5 seconds for a velocity of negative 10 meters per second. Okay, if we draw that out, it's going to look like this. We have all the way down here, we change our velocity at 15 seconds to negative 10. So it's at negative 10, constant velocity because of the constant slope. We go back up here somewhere. Now the next slope looks like it's negative 20 and over 5. So it looks like it's negative 4 meters per second. I know it's got to be less because this slope right here is definitely going to be not as steep. So that value absolutely has to be less, and so it is. So let's go complete this. All right, over here, negative 4, beautiful thing. And we also have a flat slope over here. Let's clean up a little bit so you can see exactly what that is. Okay, get this stuff all off. All right, and over here we see that this is a flat slope, therefore 0 meters per second. All right, and this is the final graph. This is what it should look like. So we've successfully encoded information, the same motion information. We're looking at it from a different perspective. Instead of our position, we're looking at it in terms of the speed. We know that the slopes mean constant. The constant slope means constant velocity. And so there we go. It's looking pretty good. All right, that's what it is. And so what I say is that this is Morad. Ooh, look at these things. And I'm gonna sign off. Here we go. Like this. Morad out.